Okay, so we now want to take a look at situations where we have a composition of three or more functions, where we have to apply the chain rule two or more times. So for example, suppose I'm taking the derivative, and this looks pretty complicated here, but follow me here. We have three functions, f, g, and h. H is the innermost function. So we're taking the function h, plugging the output to the function h into the function g, right? And there's the composition, first of all, inside here. And then we take that output and plug it into the function f. So we've composed twice. Okay. Another way of thinking about this is I have an outer function of f. Let me cover up the inner function, right? The outer function is f, and so it's chain rule. I take the derivative of the outer function, f prime, evaluate the inner function. What's the inner function? It's g of h of x, right? G of h of x. So at g of h of x, right? So f prime g of h of x. But then we take what? The derivative of the inner function. Well, when we look at the inner function, we say, hey, that's a composition as well. So you see how you have to use the chain rule there. So again, I have the outer function g, its derivative, right, times the derivative of the inner function, h prime of x. So it's chain rule essentially twice. In other words, when I apply the chain rule and I take the derivative of the inner function, it's a chain rule as well. And the idea is, right, we just keep going on. You know, suppose inside, after we do the derivative of g, we get g prime. Suppose h was a composition of two functions. Well, then I'd have the chain rule again, right? So you can have four functions composed together, and I'd have to use chain rule three times. But each time, right, we're multiplying or adding on another link to this long chain. I don't know if that's exactly why it's called the chain rule, but it makes sense to me. Right, we keep chaining these on. And notice each time when we take the derivative of the outer function, kind of peel it away. Right? We take the derivative of the outer function, f prime, peel it away, it's gone. Take the derivative of the outer function, which is now g prime, peel g away. Take the derivative of the inner function. All right? Once we get peeled all the way to the center, we stop. We don't do chain rule anymore. Okay? Leibniz notation, if y is a function of u is a function of v now, and v is a function of h. So u and v are kind of intermediate variables. You see how this works, right? So v is h of x. So if I replace v here with h of x, I'm going to have g of h of x. And if I replace u in here, I'll have f of g of h of x. So this is the same composition here. And now we want to find what's the derivative of y with respect to the independent variable x, dy dx. Well, remember how the Leibniz notation worked. You can write these fractions, dy du, derivative of the outermost function with respect to u, times du dv, right, because u is a function of v, and then what, dv dx. And notice, see how it works, the du's kind of cancel here, and the dv's kind of cancel, and you have dy dx. So that's why it, quote unquote, works. It's a helpful tool for remembering how to do the chain rule. And again, if we have more functions composed, we can continue on. So let's take a look at this. Okay. So tangent of secant of pi t, right? Function of t. So when we take the derivative here, it's by chain rule. So let's do that. What's the outermost function here? What's the outer function? It's the tangent, right? Tangent of something, right? So what is the derivative of the outer function? What's the derivative of tangent? Okay, and that's secant squared. Of what? Well, what's inside is secant of pi t. Right? Pi is a constant here. T is the variable. So that's the derivative of the outer evaluated at the inner. But now I need to multiply times what? The derivative with respect to t of that inner function, which is secant of pi t. So that's the chain rule, right? But when I take the derivative here, what do I have? I have another chain rule, right? The inner function is pi t, the outer function is secant. Right? So what's the derivative of the outer function in this case? What's the derivative of secant? So recall here the derivative with respect to x, we'll say, of secant x. If it was just secant x, or if it was just secant t, what would the result be? It's secant x times tangent x. If you remember, that's the derivative of secant. And so here, though, it's going to be what? Derivative of secant pi t is, secant u is the inner function, is pi t. it's going to be secant u tangent u times du dx. So it's going to be secant u, which u is pi t, times tangent pi t times what? The derivative with respect to t of the inner function pi t. So what I've done is chain rule and then chain rule inside of that. What's the derivative with respect to t of pi times t? It's just pi, right? Pi is a constant multiple. It's just a line of slope pi, right? Be real careful. I've seen this before. The derivative of secant of pi t is secant pi t tangent pi t times this, or the derivative with respect to x of secant x is secant x tangent x. This is not, I've seen students do this, secant tangent x. That doesn't make any sense. There's no such function called secant tangent. Remember, when we write secant x, it's really secant of x, tangent of x. And so that's not something you ever want to write. Okay, so going back to our result, what do we have? We have this pi is just a constant. I'm going to pull that all the way in front. Okay, and be careful here. Is this secant squared of secant pi t, does that become secant cubed pi t? Be real careful here. No, this is not multiplication here. You can't multiply by secant squared. This is secant squared of this. In other words, it's really secant of this and then square everything. So I have to leave it that way, right? This is secant squared of secant pi t and then times secant pi t tangent pi t. And there's our result. Okay. Let's try one more. Now, again, secant squared of this is really secant of this all squared. Here I've got sine cubed of e to the 5x. So it's very helpful to write this as, sine cubed of e to the 5x. So what we have is sine of e to the 5x all cubed. That's what that means. Sine cubed of this stuff is sine of this stuff cubed. So that's shorthand notation. This is more helpful. This notation here will help us with the derivative. So when I find g prime of x, what do I have? The outer function is u cubed, right? Something cubed, the cubing function. You see that? That's the outermost function. What's the derivative? Bring the 3 down, u to the second power. So I bring the 3 down, u to the second power. What's u? Well, it's just sine of e to the 5x. So times what? The derivative of what's inside. Right, there's chain rule. Okay. Or generalized power rule, right? 3u squared. But when I take the derivative here, what do we say? Hey, there's another chain rule. There's another chain rule. So the outer function now is sine. The inner function is e to the 5x. So what's the derivative of sine? It's cosine. Evaluated at the inner function, right? Times what? The derivative with respect to x of the inner function. Okay. So let's just write out what we have so far here. I've got 3 sine of e to the 5x all squared. That's going to be sine squared of e to the 5x. That's the way I can write that. Times what? Cosine e to the 5x. Put that in parentheses. Don't have to, but let's do that. Times what? Times the derivative with respect to x of e to the 5x. Okay, so let's just write that derivative with respect to x of e to the 5x. But now what do we realize about this thing here when we take this derivative? Well, yes, indeed, it is chain rule again. Third time, right? So we started u cubed, that was a chain rule, 3u squared times du dx. when I took the derivative of u now, the inner function there, it's a chain rule. Sine is the outer function, derivative of sine is cosine, times the derivative of the inner. And then when I take this derivative of this inner function here, it's chain rule again. I've got e to the u, right? So it's the derivative of the outer function, e to the u, derivative is e to the u, times the derivative with respect to x of the inner function, which is 5x, right? Now, is this chain rule here? Derivative with respect to x of 5x? No. That's just 5, right? That's just linear function, line of slope 5, or constant multiple rule. Pull the 5 out, derivative of x is 1. And so we're done. You say, when is this process done? We've peeled away the layer, so to speak. We got to the innermost function that's not a composition of 2 or more functions. So finally, this 5 e to the 5x times 3 gives me 5 times 3, 15 e to the 5x. Let's pull that out in front. Sine squared e to the 5x cosine e to the 5x. So there was an example where we had to use the chain rule 3 times. Okay. Okay, so we can have lots of combinations, and so you want to certainly practice the homework. Lots of ways where you have chain rule inside a chain rule, quotient rule inside a chain rule inside a product rule, etc., etc. Lots of variation there. So you want to just keep practice so you learn how to incorporate those rules into finding the derivatives. Okay. I want to switch gears a little bit now that we've talked a little bit about compositions and the chain rule, and just graphically see if we can figure things out. We've done some of these before. Here I have the graphs of 2 functions. F is the solid line and g is the dashed line. And they're basically piecewise defined functions. I'm not asking you to come up with formulas for them, which they would have basically they're linear functions for each of their portions. You don't have to do that. It's not what I want you to do. I just want you to use these graphs to estimate the following. First of all, I'll let h of x be what? This is f of g of x. This is not a product. This is a composition. Notice the difference. It's not f of x times g of x. That would be a product. This is a composition. And we're going to use the graphs above to estimate h prime of 0. So in order to find h prime of 0, I first have to find h prime of x. You have to find the derivative, and then you can plug in. So how do I do that? Well, I'm going to do it from this, which is the what? Composition means chain rule, right? F is the outer function, g is the inner function. Derivative of the outer function, evaluate the inner, times the derivative of the inner. So it's basically just the chain rule. There's the formula for h prime of x. So that means now I can plug in. So h prime of 0 is f prime g of 0 times g prime of 0. Okay. So first of all, I need to know what is g of 0. How do I find g of 0? Well, g is the dashed line here, right? What is g of 0? So it's simple. Input 0 when x is 0, what's the output? Negative 4, right? Point 0 comma negative 4 is on the graph of g, so g of 0 is equal to negative 4. And then g prime of 0, what's g prime of 0? Remember, that's the slope of the graph at 0. Well, at 0, what's the slope of the graph? What's the slope of the tangent line? It would coincide with the graph of the function of this line segment. So what's the slope of this line segment? It's obviously negative, since it's going down from left to right, decreasing. If I go from one point to another point, I go down 1, 2 over 1. Down 1, 2 over 1. So the slope is negative 2. So does everyone see, hopefully, how I'm getting these values from the graph of the function above? And so what do I have? I have negative 2 times f prime of negative 4. So notice I still have one more thing to do. I have to figure out what is f prime of negative 4. Well, now I'm looking for the slope f prime of the function f at negative 4. So f was the solid line at negative 4. What is the slope of this line? What's the slope of this line? I hope you're saying it's negative 1, right? Down 1 over 1, down 1 over 1. Yeah, it's negative 1. So the slope of that is negative 1. So now I just multiply negative 2 times negative 1 gives me positive 2. So there's my answer. Let's try a couple more. If p of x is equal to f of x squared, let's find the value of p prime of negative 1. So p of x is f of x squared. First find the derivative. Again, it's going to be by the chain rule. Outer function again is f, like above, but now what's the inner function? X squared. So what's the rule for the chain rule? Derivative of the outer function, f prime, evaluated at what? The inner function, times the derivative of the inner function. Right? And what is the derivative with respect to x of x squared? It's 2x. So my answer is 2x f prime of x squared. That's my derivative. Okay. So now I can evaluate it, right, at what? Negative 1. So it's 2x is negative 1, 2 times negative 1. F prime, and be careful here, negative 1 is being squared, and what happens when I square negative 1? That becomes positive 1, right? This becomes positive 1. 2 times negative 1 is negative 2 f prime of positive 1. So after I simplify, what do I need to find from the graph above? The slope of f, right, f prime, at 1, at x equal 1. What's the slope of the function f, right, solid line, at x equal 1? What's the slope of this line segment? What's the slope of that line segment? It's positive, right? It's going up from left to right. And what are we doing? Going up 1 over 1, 2. Rise is 1, run is 1, 2. 1 divided by 2. It's a half, right? F prime of 1 is 1 half. Negative 2 times 1 half is equal to negative 1. Okay. So again, we're not asking you to find formulas for f and g and find a formula for p of x in terms of those formulas. No, nothing like that. Just straight up using the chain rule and then plug in. Last one. My first thing here, finding the s prime of 6 if s of x is the square root of g of x, is I would write s of x as what? G of x all raised to what power? 1 half. Right? So when I find s prime of x, it's by the power rule, generalized power rule really, right? Because it's u to the 1 half. So the outer function is 1 half, u to the 1 half, I bring a 1 half down. U is g to the x, the inner function. Subtract 1 from a half, negative 1 half, times the derivative of the inner function is what? G prime of x. And I can clean this up because this g of x to the negative 1 half is 1 over g of x to the positive 1 half, which is 1 over the square root of g of x. So this becomes, up top, g prime of x. Down below I've got a 2, and this becomes square root of g of x. So now we're ready to find s prime of 6. G prime of 6 over 2 times square root of g of 6. Okay. Well, it's g prime of 6. That's the slope of g at x equals 6. What's the slope of g, the dashed line, at x equals 6? At x equals 6. Again, we're not going to fool you. We're assuming this continues on in that direction. So right there at 6, what's the slope of this line? It's positive, right? It goes up 1, 2 over 1, up 1, 2 over 1, up 1, 2 over 1. Slope is 2. So the top is 2. The bottom is the square root of g of 6. Now we find, g of 6, we now find the output to the function g at x equals 6. What is the output to the function g at x equals 6? That's the easy part. Just what is the output? It is 4. G of 6 equals 4. b of 6 equals 4. So it's the square root of 4. Of course, the square root of 4 is 2, and I get 2 divided by 2 times 2, 2/4. 2/4 is what? 1/2. And there's my result. Okay. All right, so chain rule is going to be fairly prevalent, and we've got to practice with that. So I would start, really working. In the homework, sometimes you'll see, you'll get to a point where it'll say, find the derivative using any rules that you've developed so far. And so that's where it gets interesting. That's where you're going to have to be able to really think about which rules apply and how am I going to find the derivative. Can I simplify and rewrite it some way? We've seen some examples of that. But that's what you'll need to do as you begin to practice those. Okay, that's it for the chain rule.